1999, October 1st, Beijing. A military parade crosses Tiananmen Square for the 50th anniversary of the People's Republic, and something unfamiliar appears on the cobblestones. Angular silhouette, a big welded turret, aggressive hull lines. This is the Type 98, China's first real attempt at a third-generation main battle tank. And nobody outside a handful of classified bureaus has seen it until now. Western military attachés in the crowd are already snapping photographs, trying to catch every angle. It's worth understanding where China's tank program stood at the time. Through the late 1980s, the PLA was still running vehicles built on Soviet blueprints from the 1950s and 60s. The backbone of the fleet was the Type 59, essentially a licensed copy of the T-54, and by the standards of the late Cold War, it was hopelessly outclassed. Chinese military planners were well aware that in a serious armored engagement, these vehicles would be torn apart by anything fielding modern fire control and composite armor. The first serious effort to close that gap was the Type 90 project. The Chinese had gotten hold of a T-72, reportedly through intermediaries in the Middle East. It was trucked to a test facility, stripped to the last bolt, and every component was documented and reverse-engineered. The resulting vehicle, designated Type 90, looked decent on paper but disappointed in practice. Even after fitting it with a Western-sourced fire control system, the tank fell short of what a modern MBT needed to be. The running gear gave constant trouble. The engine lacked the output for real tactical mobility, and the armor package was thin by contemporary standards. Beijing made a pragmatic call. The Type 92 wasn't good enough for PLA service, but it could be exported. In May 1990, a production deal was signed with Pakistan, and the vehicle eventually became the Al-Khalid. Meanwhile, the engineers went back to the drawing board for a tank the PLA would actually field. That project kicked off in the early 1990s, and the team carried a clear mandate: build something that could stand across the field from an M1A1 or a T-80U and not be at an obvious disadvantage. The biggest single problem was propulsion. Chinese diesel technology at the time simply could not deliver the power-to-weight ratio a 50-plus ton tank needed. The domestic engine options maxed out at outputs that were adequate for a 36-ton vehicle, but completely inadequate for anything carrying serious composite armor. Several Chinese factories attempted to develop higher output diesels, but the results kept falling short. Either the power wasn't there, or the engines ran hot, or the service life was unacceptably short. The metallurgy for high-performance engine components, like turbocharger blades and cylinder liners, was a particular bottleneck. After considerable back and forth, they secured access to German diesel engine technology, most likely derived from the MTU MB 870 series, though a Steyr WD 396-based lineage has also been suggested. The result was an engine rated at 1,200 horsepower, which gave the Type 98 combat weight somewhere in the 50 to 52-ton range, a power-to-weight ratio above 23 horsepower per ton, competitive with the T-80U and not far behind the Abrams. Cross-country, that translated into genuine agility, the ability to reposition quickly, climb grades that would stall weaker vehicles, and maintain speed over rough terrain without overheating the drivetrain. The second key decision was the turret. Soviet lineage tanks had always used cast turrets, and the Chinese had followed suit on every previous design. But casting limits what you can do with armor geometry and layering. The process constrains wall thickness, plate angles, and the internal cavity shapes needed for effective composite fills. A welded turret threw those constraints away. You could build multi-layer composite packages from flat plates, steel of different hardnesses, ceramics, rubber, glass fiber composites, shaped and angled precisely for maximum resistance to both kinetic penetrators and shape-charged jets. The resulting frontal turret protection was estimated at 450 to 500 millimeters RHA, equivalent against heat threats, which put the Type 98 in the same general bracket as vehicles like the T-80B with Contact 1 or early T-90 variants, though still a step behind the heavy Chobham-type packages on the M1 Abrams and Leopard 2. The hull kept some of the T-72's DNA in its basic layout, but Chinese engineers reworked the upper glacis extensively, thicker plates at steeper angles with improved weld quality throughout. The lower glacis remained thinner, as on most tanks of the era, partially shielded by the track assemblies and front road wheels. The main armament was a 125mm smoothbore gun, designated ZPT-98. Its exact lineage is debated. One school of thought traces it to the Soviet Tu-A46 family via a Tu-A46M, allegedly sourced through Ukraine in the early 1990s, when a lot of Soviet military hardware was finding its way onto the gray market. Another line of argument holds that the ZPT-98 evolved from an indigenous Chinese 120mm smoothbore program and only shares the caliber with the Soviet weapon, not the internal ballistics or manufacturing process. In either case, the gun worked. The 125mm smoothbore was a well-proven caliber by the late 1990s, fielded on thousands of tanks worldwide, and the ZPT-98 could reliably punch through the frontal armor of most second-generation MBTs at realistic engagement distances of 1,500 to 2,000 meters. An autoloader, carousel type, mounted beneath the turret floor in the hull, fed the gun at around 8 rounds per minute. This was comparable to the rate a skilled human loader could sustain on a Western tank, with the advantage of consistency. The machine doesn't get tired or fumble around during a bumpy cross-country advance. There is a well-known trade-off here, though. Carousel autoloaders store ammunition in a ring around the turret base, which means the rounds sit below the crew compartment rather than in a separate bustle rack with blowout panels, as on the Abrams. If the carousel is penetrated by an incoming round, the ammunition can cook off catastrophically, a vulnerability that was demonstrated with grim clarity on Soviet-pattern tanks in various conflicts. Chinese engineers were presumably aware of this risk, but the carousel design saved significant turret volume and height, and they chose to accept the trade-off. The carousel stored a mix of APFSDS, heat, and HE frag rounds, with the crew able to select ammunition type from the gunner's station. The Chinese were also developing a gun-launched ATGM for the 125mm tube, intended to reach out to about 5 kilometers. The concept was borrowed directly from Soviet practice. The sphere and reflex systems on the T-64 and T-80 families had been in service for years, and it gave the Type 98 an option against targets well beyond standard direct fire range, including hovering attack helicopters that might otherwise stay outside the engagement envelope of a conventional tank round. The fire control system was arguably the most critical subsystem on the whole vehicle. Experience with the Type 90 had hammered home a painful lesson. A powerful gun means nothing if the targeting electronics can't keep up. Chinese optics and military electronics were the weakest link in the industrial base during the early 1990s, so the designers sourced Western components. The exact supplier has never been publicly confirmed, but the system reportedly shared architecture with the FCS used on the export Al-Khalid. It included a laser rangefinder, a digital ballistic computer that factored in barrel wear, propellant temperature, crosswind, and vehicle cant angle, and a 2-axis weapon stabilizer that allowed accurate fire on the move. The commander got a panoramic sight with independent traverse, enabling hunter-killer capability. The commander scans, designates a target, the turret slews automatically, and the gunner engages while the commander is already looking for the next threat. A thermal imaging channel gave the crew the ability to fight at night and through smoke, dust, and light rain. Though the early Chinese thermal imagers were reportedly lower resolution than their Western counterparts and had shorter effective detection ranges. The running gear was conventional. 6 road wheels per side on torsion bar suspension, a design that dates back to World War II, but remains popular because it's mechanically simple and easy to service in field conditions. Tracks used rubber metal links that offered decent service life across different terrain types, from paved roads to rocky mountain trails. Top speed was above 65 kilometers per hour on road, and operational range sat between 450 and 600 kilometers depending on terrain and driving speed without auxiliary fuel tanks. External fuel drums could be fitted to brackets at the rear of the hull for long marches, a practical necessity in a country where an armored unit might need to transit hundreds of kilometers of open steppe or mountain roads just to reach its operational area. The German-derived diesel handled altitude and temperature extremes without major complaints, which mattered enormously given the range of Chinese terrain, from the thin air of the Tibetan Plateau above 4,000 meters to the winters of Manchuria where temperatures regularly drop well below -30 Celsius. 3-man crew, commander, gunner, driver, no loader. The autoloader handled that job, which kept the fighting compartment compact and the overall vehicle weight down. Crew stations had modern observation devices and periscopes. Communications ran through a radio set with a rated range of about 30 kilometers, plus an intercom for the crew. The NBC protection system used a filtration unit and automatic sealing, with sensors that would detect chemical or radiological contamination and trigger collective protection mode without crew intervention, a feature reflecting Cold War-era anxiety about nuclear escalation that still shaped Chinese military thinking well into the 1990s. Now, the turret design is where the Chinese made their biggest leap relative to everything they'd built before. If you compare photographs of the Type 98 turret to the cast turrets on the Type 69 or even the Type 80, the difference is stark. The front of the welded turret had a layered structure. Outer and inner plates of high hardness rolled steel with a filler material between them, chosen specifically for its ability to disrupt and absorb the energy of a shaped charged jet. Here's how that works in practice. A heat warhead detonates against the outer plate, and the resulting copper jet, traveling at several kilometers per second, begins to bore through the steel. When it hits the filler layer, the material's physical properties interfere with the jet's coherence. The jet spreads, fragments, and loses penetrating power before reaching the inner plate. The composite sandwich, combined with plate angles that force the jet to travel through more material than the raw thickness would suggest, pushed effective heat protection well above what you'd get from an equivalent weight of plain steel. In photographs, you can see that the frontal armor packages were modular, separate bolt-on sections rather than a single monolithic block. That was a deliberate engineering choice with real operational benefits. A module damaged in combat could be unbolted and swapped in the field, getting the tank back in action without a factory visit. And as new armor materials became available down the line, the modules could be upgraded without touching the rest of the turret structure. A built-in future-proofing feature that cast turrets simply cannot offer. Compare that to the progression on Soviet tanks during the same period. Early T-72 models, the ones that performed poorly against coalition forces in the 1991 Gulf War, had simple cast turrets. Thick steel, adequate against kinetic rounds at range, but no special provision against heat. The T-72A brought a significant improvement. Cavities inside the casting were filled with a non-metallic material, commonly called sand rod inserts, that did a decent job of disrupting shaped charged jets. But the casting process limited how far you could push the geometry, and the turret shape remained dictated by what the foundry molds could produce rather than what would be ideal for ballistic protection. The T-80 family got thicker castings overall, and on later variants, bolt-on Contact 1 ERA tiles that helped considerably against heat threats. but ERA was a bolted-on solution to a fundamental design limitation. It added weight, complicated maintenance, and posed a fragmentation risk to nearby infantry. The Chinese, by going straight to a welded composite turret, effectively skipped those intermediate stages and went directly to an approach that Western nations had adopted a full decade earlier with the M1, Challenger, and Leopard 2 programs. The turret sides were thinner than the front, as on every tank, because you can't armor everything equally without the weight becoming prohibitive. But they offered protection against 30mm autocannon fire from IFVs and against artillery fragments, which are statistically the most common threats to a tank's flanks on a modern battlefield. The roof was reinforced specifically against cluster munitions, which by the 1990s had become a core element of NATO anti-armor doctrine and represented a serious top-attack threat. The rear of the turret was the lightest zone, housing maintenance access hatches, stowage points for crew equipment, and antenna feeds with enough armor to stop small arms and light shell splinters, but not much more. On top of the turret sat the commander's cupola with observation devices and a hatch, plus the gunner's hatch. A 12.7mm heavy machine gun was mounted in front of the commander's position for air defense and engaging infantry in the open. A coaxial 7.62mm machine gun, bore-sighted to the main gun, handled lighter targets. Banks of smoke grenade launchers were fitted on the turret sides. Push a button on the console, and the grenades fly out several dozen meters, popping into a thick white screen that blocks both visual observation and the guidance systems of many semi-active laser-guided missiles. The system could be triggered manually by the crew or automatically when the laser warning sensors picked up a targeting beam. And that brings us to the JD-3, the single most talked about feature of the Type 98, and also the one that Western analysts spent the most time arguing about. Unlike a conventional active protection system that physically intercepts an incoming round with a launched countermeasure, think Arena or Trophy, the JD-3 took a directed energy approach. A laser warning receiver mounted on the turret roof behind the commander's position detected when the tank was being illuminated by an enemy laser, a rangefinder, a designator, a missile guidance beam. The turret could then be traversed toward the source, and a high-powered laser emitter mounted in a boxy housing behind the gunner's hatch would engage the threat. The stated capabilities included damaging or blinding enemy optical systems, disrupting the guidance links of beam-riding anti-tank missiles, and even dazzling the pilots or sensors of low-flying attack helicopters. At the time, no Western tank carried anything like it, which is partly why it drew so much analytical attention and so much skepticism about whether it actually worked as advertised under real combat conditions, a question Chinese sources showed no interest in answering publicly. After that October 1999 parade, intelligence agencies from several countries scrambled to figure out how many Type 98s existed and what they could really do. The picture that emerged was unexpected. There weren't many. The Type 98 had never been intended for mass production. The Chinese military treated it as a pre-production platform, a way to prove technologies and work out integration problems before committing to a full production vehicle. Total output was probably a few dozen hulls, maybe fewer. The reasons were practical. The tank was expensive, and most of that cost came from imported content. The German engine and the Western fire control components together accounted for a huge share of the per-unit price. At the production volumes China could manage in the early 1990s, there was no economy of scale to bring the cost down to anything the PLA's budget could absorb across hundreds or thousands of vehicles. Beyond cost, the troop trials turned up real engineering problems. The running gear wore faster than specifications predicted under sustained field use. Certain drivetrain components had premature failure rates that pointed to metallurgical or machining quality issues in the domestic supply chain. The fire control system was accurate but temperamental. sensitive to dust and vibration in ways that made it hard to maintain under field conditions without trained specialists and clean workshop facilities. Every one of these problems became a line item in the requirements document for the next vehicle. The Type 98s that were built went to several units for intensive operational testing. Crews had to learn a completely different way of operating a tank. The Type 59 was a fundamentally simple machine. Any trained mechanic with a standard wrench set could keep it running indefinitely. The Type 98 demanded people who understood hydraulic systems, digital electronics, thermal optics, and computerized fire control diagnostics. The PLA set up dedicated training centers specifically for these crews and their maintenance teams, which was itself an institutional change as significant as any hardware upgrade. Officers who had spent their entire careers on Soviet-pattern tanks had to relearn fundamental habits: how to conduct pre-combat checks on a vehicle with digital systems, how to troubleshoot a thermal sight that won't calibrate, how to swap an autoloader component without damaging the delicate feed mechanism. It was a culture shift as much as a technical one. By the early 2000s, the production version was ready. Designated Type 99, it looked a lot like the Type 98 at first glance. Same angular welded turret, similar hull proportions, familiar silhouette. But the differences went well beyond cosmetics. The most visible external change was the addition of ERA blocks, covering the frontal arc of the turret and upper hull. These rectangular containers, each holding a slab of explosive between steel plates, gave the tank a distinctive heavy-browed, bristling appearance. On impact from a heat round, the explosive detonates, the plates blow outward, and the incoming jet gets disrupted and scattered before it can reach the composite armor underneath. Against kinetic penetrators, the benefit was less dramatic, but the additional layer measurably improved survivability across the threat spectrum. Under the engine deck, the Type 99 received an uprated diesel, putting out 1,500 horsepower. It was manufactured at Chinese factories using MTU, derived technology under license, not a fully independent Chinese power plant, but domestic production was a major milestone regardless. It cut the dependency on direct imports from Germany, simplified the logistics chain, and made it feasible to build engines at the volume a mass production program demanded. The electronics underwent a parallel transition. After years of heavy investment in defense sector electronics, Chinese industry could now produce thermal imagers, laser rangefinders, and ballistic computers that met the PLA's acceptance standards. They still weren't at the level of the best American or French systems in terms of detection range and image resolution, but the gap had narrowed to the point where it was no longer a disqualifying weakness. The PLA was willing to accept the domestic kit and upgrade incrementally rather than remain dependent on foreign suppliers who might cut off access at any time for political reasons. Production of the Type 99 ramped quickly. Where the Type 98 had been built in the low dozens, the Type 99 was coming off the line by the hundreds and going straight to elite armored divisions, displacing the aging Type 59s and Type 69s vehicle by vehicle. And the original Type 98s? They did what testbed vehicles always do once the production model arrives. As Type 99s filled the ranks, the pre-production machines were pulled from frontline service. Some went to storage depots for long-term mothballing. Others stayed in training units where they remained useful for crew familiarization, tactical drills, and maintenance instruction. Their relatively low mileage and sound mechanical condition meant they had plenty of service life left for that secondary role. The arc of the Type 98 program mirrors the broader trajectory of Chinese defense industry over the past 3 decades. In less than 20 years, the tank program went from disassembling a foreign vehicle in a hangar and trying to copy it piece by piece, through a failed first attempt and an expensive proof of concept stuffed with imported subsystems, all the way to series production of a competitive modern design built predominantly from domestic components. The Type 99 continued to evolve after initial fielding. Upgraded variants brought improved composite armor arrays, more powerful engines, and better electronics with each iteration. Some versions received active protection systems designed to physically intercept incoming projectiles, a step beyond the laser-based approach of the Type 98's JD-3. Others were fitted with networked battle management systems that allowed real-time data sharing between vehicles, headquarters, and supporting arms, turning individual tanks into nodes in a larger tactical information network. Every one of those capabilities traced its roots back to work done on the Type 98. The welded composite turret, the integrated digital fire control architecture, the autoloader layout, the engine bay packaging, all of it was first validated on those few dozen pre-production hulls that rolled across Tiananmen Square in October 1999. Today, the Type 99 family forms the core of China's heavy armored capability. These tanks appear regularly at exercises and National Day parades, and they represent a level of sophistication that would have been unimaginable to the engineers who were still taking apart a borrowed T-72 with wrenches and notebooks barely 15 years earlier. Somewhere on storage bases and training grounds, a handful of their predecessors still sit. The Type 98s that proved the concept and opened the door for everything that came after. What makes this particular story worth telling is the pragmatism behind it. The Chinese recognized the Type 90 had failed and cut their losses instead of doubling down. They bought foreign technology where they had to and invested in building domestic alternatives where they could. They built a small batch, tested it relentlessly, documented every failure, and fed all of that data straight into a better design. In a handful of years, they covered technical ground that had taken other nations decades to traverse. The Abrams, for instance, went through nearly 15 years of development, from the XM1 prototype to a mature production vehicle. The Chinese compressed a comparable learning curve into roughly half that time, partly by borrowing what they could, but also by being willing to build something imperfect, learn from it, and move on without sentiment.